everyone. In this video, we are going to learn how to find the solution of linear non-homogeneous recurrence relation with constant coefficient using operator method. In this case, we are going to use the operator as the shift operator. First, we will learn what do you mean by shift operator, and after that, we need two concepts, that is, what do you mean by forward difference and the factorial polynomial. After covering these three topics, we will move directly towards the solution of linear non-homogeneous recurrence relation. Let's move towards the first operator, that is the shift operator. As the name suggested, shift means it is going to shift something. When we are using a shift operator on any function, it shifts that function with some steps. Means if I am going to apply a shift operator on a function f, that is depending upon x, then it will shift the function with some step, that is x plus h. Now the pointer shift operator is represented by which symbol? Basically the shift operator is represented by capital E. It means it will shift the x with x plus h, where h is a step size. But in sequence, there is no need of h, as we know that the sequence starts from A0, then A1, A2, A3, A4, and when we want to shift A0, it means it will move towards the A1. And if you want to shift A1, it will move towards the A2. It means the index is changed by 1. So therefore, when you apply a shift operator on an, the index is shifted, that is by 1, n plus 1. And if we write e square of an, it's like we are operating shift operator twice on an term. So for this, we can write this is an plus 1, and one shift operator is as it is. Again shift this one, that will give you an plus 2. So in general, when we write e raised to power k an, it shift the index as n plus k. तो शिफ्ट ऑपरेटर जितनी बार अप्लाई करोगे उतनी बार स्टेप्स इंक्रीज होंगे. एज n के बाद कौन सा स्टेप है? n प्लस 1. सो इट विल शिफ्ट दिस इंडेक्स n टू द n प्लस 1. अगर हम k टाइम्स शिफ्ट ऑपरेटर अप्लाई कर रहे हैं, इट मीन्स ये जो इंडेक्स है वो k स्टेप आगे चला जाएगा, दैट इज n प्लस k. नेक्स्ट टर्म इज द फॉरवर्ड डिफरेंस. Forward difference is represented by delta. Now, forward difference, we can split this into two parts. One is a forward and then difference. Simply, if I say take a difference from the forward steps, that is called as a forward difference. And when we are applying the same concept on an, it means one step ahead we need to move forward, that is n plus 1. Now take its difference from the current position. So simple, as per the word name suggested, forward difference means we need to take one step ahead and then we need to take the difference. Right now we are at an and an plus 1 is a forward step, then take its difference. Similarly, we have the backward difference as well. Backward difference means if I am standing at an, we need to move back, that will be an minus 1, and then take its difference, that is an minus 1. That gives you the backward difference. But we just need the forward difference, not a backward difference. Now we can also write this an plus 1 in terms of an. How? Basically, in this case, the index is shifted by 1 when we are applying shift operator on an. So we can write this an plus 1 as a shift operator on an, and this is as it is delta of an as it is. From here we can take an outside. We have e minus 1 an delta of an. Now this is an operator. Also shift is an operator. So from here we are getting delta is equal to shift operator minus 1, or we can say shift operator is equal to 1 plus delta. So here we have the relation between the forward difference and the shift operator, that is shift operator is equal to 1 plus forward difference. Now moving towards the concept of factorial polynomial, it is similar to the factorial. Again we can break this word into two parts. Factorial means like n factorial, or we can say that 4 factorial. This means 4 into 3 into 2 into 1. And when we write 5 factorial, it is 5, 4, 3, 2, 1. So product of these one is equal to the 5 factorial. N factorial means n, n minus 1, n minus 2, n minus 3, continue till 2, 1. This is the meaning of n factorial. But we need a factorial polynomial. Now we will club factorial with polynomial. How? Factorial polynomial means when I say n raised to power 1 factorial, it means we need a polynomial with the help of factorial, and from here we will just take one term, that is first n. When we write n raised to power 2 factorial polynomial, it means we need a polynomial from the factorial by taking only first two terms, that is n, n minus 1. N raised to power 3 factorial polynomial means we need a polynomial from the factorial by taking first three terms. First term is n, next term is n minus 1, its next term is n minus 2. And when we say n raised to power 0 factorial polynomial, it means that is equal to 1. Now we can write the general formation of the factorial polynomial, that is n raised to power m factorial. It means we need m terms from this factorial. First term is n, next is n minus 1, then n minus 2, then n minus 3. We have taken 4 terms. We need m terms. Continue till n minus m minus 1. You get the pattern from here. When we are working with n raised to power 2 factorial polynomial, we are getting the term till n minus 1. When we are taking n raised to power 3 factorial polynomial, we are getting the term last as n minus 2. And here we have mentioned n raised to power m. That means here we have m minus 1. Next we will cover what is the relation between general polynomial and factorial polynomial. In general polynomial, first we have the constant term. Suppose the constant term is 1. That can be written in form of factorial polynomial as n raised to power 0. Whereas if I say n, that is written as n raised to power 1 factorial polynomial. Because n raised to power 1 factorial means we need only one single term from the factorial, that is n. And if you need to write n square, that can be written as n raised to power 2 plus n raised to power 1 factorial polynomial. How we are getting this one? It's very simple. We will start from the factorial polynomial n raised to power 2. As per the definition, this is equal to n into n minus 1. Multiply this. This is n square minus n, and on other side we have n raised to power 2 factorial polynomial. From here, find the value of n square. So we can write n raised to power 2 factorial polynomial. Take this term on the other side, that is plus n is equal to n square. Now what is the value of n in terms of factorial polynomial? That is n1. So we can write n raised to power 2 factorial polynomial plus n raised to power 1 factorial polynomial is equal to n square. So from here we can say that n square is equal to n raised to power 2 factorial polynomial plus n raised to power 1 factorial polynomial. This is the derivation of this. We can also verify this, how this is equal to n square. As per this one, n raised to power 2 factorial is equal to n into n minus 1 plus n raised to power 1 factorial polynomial means simply n. This is equal to n square minus n plus n, and that is equal to n square. It means this form is correct. This is only for the verification, but the derivation is this. Similarly, we can write n cube is equal to n raised to power 3 factorial polynomial plus 3 times of n raised to power 2 factorial polynomial plus n raised to power 1 factorial polynomial. Now let's write this one. So n cube can get when we are dealing with n raised to power 3 factorial polynomial. This is equal to n into n minus 1 into n minus 2. Multiply this, keep this n as it is. This is n square minus 2n minus n plus 2. This is equal to n into n square minus 3n plus 2. Further multiply this, we have n cube minus 3n square plus 2 of n. From here, we can find the value of n cube. N cube is equal to what? So it is n raised to power 3 factorial polynomial. Take these two terms on the left side. We have plus 3n raised to power 2 minus 2n. Now write the value of n square and n in terms of factorial polynomial. We have n raised to power 3 factorial polynomial plus 3 times of n2 plus n raised to power 1 factorial polynomial minus 2 times of n is replaced by n raised to power 1 factorial polynomial. Simplify this. This is equal to n raised to power 3 factorial polynomial plus 3 times of n raised to power 2 factorial polynomial plus 3 times of n raised to power 1 factorial polynomial minus 2 times of n raised to power 1 factorial polynomial. And this is equal to n raised to power 1 factorial polynomial. 3 into n raised to power 2 factorial polynomial as it is, n raised to power 3 factorial polynomial as it is. This is the proof of the last form. So we need to learn at least these 4 values of general polynomial in terms of factorial polynomial for finding the particular solution for non-homogeneous recurrence relation. Next we have the relation between forward difference and the factorial polynomial. Forward difference is represented by delta, and in case you are applying this forward difference on the factorial polynomial m, what is the value of this one? To answer this, let's start with m is equal to 1. When m is equal to 1, what we have? Delta n raised to power 1. This means this is a factorial polynomial with the degree 1, that is delta n. Now, when you are writing forward difference of n, means we need to take one step ahead, that is n plus 1 minus current position, that is n. This is equal to 1. Now when you take m is equal to 2, what we have? Delta of n raised to power 2 factorial polynomial. This is equal to what? We can write this as, we need two terms from the factorial. First is n, next is n minus 1. According to this, when we are applying the forward difference, means first we will take next step, then take its difference from this position. Next step means replace n with n plus 1, and even in this case replace n with n plus 1, and this minus as it is, minus from the current position, that is n into n minus 1. This is equal to n plus 1 into n minus n into n minus 1. So we can take n common. We have after that n plus 1 minus n minus 1. So here this n is get cancelled with this. This is equal to n times of 2, that is 2 of n. And if we take m is equal to 3, in this case delta over n raised to power 3 factorial polynomial, this is written as delta of n into n minus 1, n minus 2. Now apply delta over this polynomial. It means first we need to take the next step, then subtract from the current position. Next step means n is changed to the n plus 1. Even in this case, even in this case. So we have n plus 1 into n plus 1 minus 1 into n plus 1 minus 2. This is the meaning of the next step, minus current position is n into n minus 1, n minus 2. Simplify this. This is n plus 1 into n. It is n minus 1 minus n into n minus 1 into n minus 2. So here we have two terms as a common, that is n into n minus 1, and the remaining term is n plus 1 minus this, that is n minus 2. So this n is get cancelled with this. This is plus 1 plus 2, that is equal to 3 into n minus 1. Now this is equal to what in terms of factorial polynomial? This is equal to 3 times of n raised to power 2 factorial polynomial. Even in the previous case, we can write this is 2 into n raised to power 1 factorial polynomial, and this is n raised to power 0 factorial polynomial. You can check it whenever we are applying forward difference on the factorial polynomial, we are getting a similar form of a differentiation. In this case, if we take the derivative of n cube, that is equal to 3 into n square. But in this case, it is a factorial polynomial. Rather than writing 3 into n square, we write 3 into n raised to power 2 factorial polynomial. Even in this case, derivative of n square is 2 into n. But it is a factorial polynomial. We can write 2 into n raised to power 1 factorial polynomial. So in general, we can write when we are applying forward difference on the factorial polynomial, this is equal to m times of n raised to power m minus 1 factorial polynomial. So this is similar to the differential operator. Also note that when we write 1 by delta n raised to power m factorial polynomial, this is equal to n raised to power m plus 1 by m plus 1. With the same concept, we can derive this formulation. It works like an integration, like here it works as a differentiation. And this is only for the forward difference over the factorial polynomial, not for the general polynomial. Now we are in a position to discuss the solution of linear non-homogeneous recurrence relation with constant coefficient. Here we have taken the general form of recurrence relation where an is calculated with the help of previous k terms plus some extra function is there. It means the degree of this recurrence relation is k. How? That is, you can calculate the difference between highest index, that is n here, and the lowest index in this case is n minus k. So take the difference of these two one, that will give you the degree of the recurrence relation as k. Here we have taken the extra function. Due to this, we call it as non-homogeneous recurrence relation. First step in this case, take all the sequence term on the left side, means take C1 a n minus 1, this term, this term, this term on its left side, and the sign is changed in this case. In the next step, we need to remove the negative index if it contains, like negative index as n minus 1, n minus 2, n minus 3, n minus k. Basically, our requirement is minimum index in this recurrence relation should be an. For that, we will use the concept of shift operator. How? In this case, if we apply the shift operator one time on the term an minus 1, this will give you a of n. And in this case, how we can reach to the an? That is, if we apply shift operator twice. In this case, we need to apply the shift operator 3 times, and here we need to apply the shift operator k times. So we need to apply maximum by k times shift operator to get as minimum index as an. So second step is always identify minimum index. As per this one, the minimum index is n minus k. Accordingly, we will apply the shift operator. So applying shift operator k times on both sides. When we are applying the shift operator, we need to apply on the right side function as well. This is very, very important. So after that, we can distribute this shift operator on each and every term. So it is like e raised to power k of an. Here it is e raised to power k over this term. Then e raised to power k over this term. At last, e raised to power k term over an minus k. We will take constant outside because it is not depending upon the index n. Now, after applying the shift operator, it can be written in this form. What we have done in this step, we have replaced n to n plus k. So this n is shifted to n plus k. Here n is shifted as n plus k, this negative of 1 as it is. Here n plus k minus 2 as it is. And in last, n plus k minus k. Also shift this n as n plus k. After that, we need to rewrite this one in form of shift operator because we need each terms in terms of an. So here we can write an is shifted k times, that is e raised to power k an. And here an is shifted by k minus 1 term. Here an is shifted by k minus 2 times. At the last, this k is get cancelled with this k. So there is no shifting. So that's why we have mentioned as it is. This right hand side function as it is. Now we can collect coefficients of an, that is e raised to power k. Here negative of e raised to power k minus 1. Here negative of e raised to power k minus 2. And last is constant ck is equal to this. From here, it is like a function of e. An is equal to a function of n plus k, where capital F of e means it is a polynomial in terms of e. Now we can find the solution of linear recurrence relation. So we can divide this into two parts. First thing, we can write the characteristic equation by writing f of e is equal to 0. From here we will get homogeneous solution of the recurrence relation that we have already covered in the previous video. And second thing, we need to find from here as the particular solution, that is evaluated as 1 by the operator form f of e over the function n plus k. And this is the particular solution. And the final solution from here we can write it as general solution of the recurrence relation is equal to homogeneous solution plus particular solution. In this video, we will learn how to find the particular solution specifically for the two cases. The first case is if we have the right hand side function of the form b raised to power n, or maybe it is multiplied by some constant b raised to power n, or it is b raised to power n plus p. What does it mean? It is like constant raised to power n. If we are getting any constant power n, or some constant is multiplied, or maybe power is n plus 4. In such case, how to evaluate the particular solution? Simply, in place of E, we will substitute B and make sure f of B is not is equal to 0. So we can call it as a case 1 when we have the constant raised to power n. So in that case, operator is replaced by the constant term. And if it is a case of failure, means f of b is equal to 0. In such case, firstly we will write this function, means this polynomial, in factor form. If we are getting in this factor form, the particular solution is evaluated as n raised to power k factorial polynomial divided by k factorial. Now we are adding something here. So we need to subtract, that is, from the power we will subtract that index. And after that, we need to expand this factorial polynomial. That is, we need k terms from the factorial. First term is n, then n minus 1, n minus 2, and the last term is n minus k minus 1, divided by same k factorial b raised to power n minus k. This is further is equal to nck b raised to power n minus k. So either write in form of the factorial polynomial form, or you can take the help of combination to write the answer. Ultimately, you will get this form. Let's understand with the help of example. The first example we have, solve the recurrence relation this. So here we have this recurrence relation. First step, we will take all the sequential term on one side. So we can write this is equal to an minus 6 of an minus 1 plus 9 times of an minus 2 is equal to 5 raised to power n minus 1. In this case, first step is eliminate negative index if it contains. It has n minus 1, n minus 2. So we need to remove the negative index. So minimum times we need to apply the shift operator is 2. So we write apply shift operator twice. So we have in this case, we can directly write here as e square an minus 6 times of e square over an minus 1 plus 9 times of e square over an minus 2. This is equal to e square 5 raised to power n minus 1. This implies here index is shifted by 2, an plus 2 minus 6 is constant. Here index is shifted by n plus 2 minus 1 as it is, plus 9. This is an plus 2 minus 2 is equal to 5 raised to power n plus 2 minus 1. What we have done in this case, when we have applied the shift operator twice, your index n is shifted as n plus 2. So here n is there, so replace by n plus 2. Here it has n, so we can replace n with n plus 2. This n is replaced by n plus 2. Even it contains n, so here n is replaced by n plus 2. Simplify this. This is equal to an plus 2 minus 6 times of an plus 1 plus 9 times of an, that is equal to 5 raised to power n plus 1. Now we need to go back to the shift operator. So we can write this is equal to e square of an. Means an is shifted by 2 steps. Minus 6. Here it is e raised to power 1 an. There is a no shifting form, so we will keep it as it is. This implies collect the coefficients of an. We can write e square minus 6 of e plus 9 of an is equal to 5 raised to power n plus 1. Now from here we can write the characteristic equation. The characteristic equation is e square minus 6e plus 9 is equal to 0. Means right hand side function is 0. As we have discussed in the previous video, characteristic equation in form of r. So we can replace e with r, or you can keep it as it is. Here we can write r square minus 6r plus 9 is equal to 0. Now what are the roots in this case? So roots in this case is 3, 3. So both the roots are real as well as equal. This implies homogeneous solution of the recurrence relation is equal to first constant, first root raised to power n plus second constant, second root raised to power n, but both the roots are same, so multiply by n. From here we can find the particular solution. How to find that? First thing, we need to take this operator form in a denominator. We can write an raised to power p for the particular solution as 1 upon e square minus 6e plus 9 5 raised to power n plus 1. Now this is constant raised to power n plus some constant. So ignore this constant. We can directly treat it as b raised to power n form. And in this case, the value of b is 5, means constant is 5. So, replace e with constant, that is 5. So, by replacing this one, we have 25 minus 6 into 5 is 30 plus 9, 5 raised to power n plus 1 as it is. This is equal to 1 by 4, 5 raised to power n plus 1. This is the final particular solution for this recurrence relation. So overall general solution in this case is equal to an is equal to homogeneous solution plus particular solution. So homogeneous solution is this. We can write this as C1 plus C2 n times of 3 raised to power n plus particular solution is 1 by 4 5 raised to power n plus 1, and that is the final answer in this case. Taking one more example, we need to solve this recurrence relation. First step is we can take all these sequential term on the left side. So we can write this as an minus 6 an minus 1 plus 9 an minus 2 is equal to 3 raised to power n. After that, we need to remove the negative index. So for that, again observe the sequential term. Here we have an minus 1, an minus 2. So minimum index is getting n minus 2. So we will apply the shift operator 2 times. So it means as per the shift operator, index n is replaced by n plus 2. So we can write it as a n plus 2 minus 6. Here a n plus 2 minus 1 plus 9 a n plus 2 minus 2 is equal to 3 raised to power n plus 2. So we can directly apply the shift operator by just changing n by n plus 2. This is equal to an plus 2 minus 6 of an plus 1 minus 9 times of an is equal to 3 raised to power n plus 2. So here we have plus. Now write this back into the shift operator form. So we can write this as e square an minus 6. Here we have used the shift operator 1, so we can write e of an. This is simply an. There is nothing in a plus. We can write simple 9 into an, not in form of shift operator. Take an common. We have e square minus 6e plus 9 of an is equal to 3 raised to power n plus 2. From here the characteristic equation is, this is e square minus 6e plus 9. As we have already done, what are the roots in this case? That is 3. We can write homogeneous solution is equal to C1 3 raised to power n plus C2 3 raised to power n into n. Now for the particular solution, we have an is equal to 1 upon e square minus 6e plus 9 3 raised to power n plus 2. Now identify, this is the case 1 again, constant raised to power n. So in this case we replace e with 3. When you replace e with 3, we have 9 minus 18 plus 9 3 raised to power n plus 2, and this quantity is equal to 0. So basically now it is a case of failure. So in case of failure, first step is write this in form of the factors. Here we know that the roots of this equation is 3, 3. It means from here we can write this is e minus 3 into e minus 3. So this equation is get converted into this form. That is, we can write this is 1 upon e minus 3 whole square, and this 3 raised to power n plus 2. After writing in a factor forms, we need to call the factorial polynomial and factorial. For that, we need to observe the power here. Here, this 3 is occurring 2 times. It means we need a factorial polynomial of order 2 divided by 2 factorial. And here we are giving something, we need to take it back. That is, in the power, we will reduce 2. N raised to power 2 factorial polynomial means we need 2 terms from the factorial, that is n minus 1 divided by 2 factorial is 2, and here we have 3 raised to power n, and this is the particular solution for this recurrence relation. So final solution for this case is homogeneous solution plus particular solution. Taking next example, here we have take the mixed case, that is a case of failure and without case of failure. Also, when we are not getting the factor of this form and one form is different, that is the constant. So we have considered all possible cases in this question. So first step, always take all the sequential term on the left side. So we can write this is as an plus 1 minus 5 times of an plus 6 times of an minus 1 is equal to 4 raised to power n plus 1 plus 2 raised to power n plus 3 raised to power n plus 5. So first step is remove the negative index. It is already in a positive index. It is also positive. And here we are getting a negative index. It means we need to apply the shift operator one time. So when you apply the shift operator once, it means n is switched as n plus 1. So replace n with n plus 1. So from here we will get an plus 2 minus 5 times of an plus 1 plus 6 times of here an is equal to, also replace n here as a n plus 1 plus 1, that will be n plus 2. So we have 4 raised to power n plus 2 plus 2 raised to power n plus 1 plus 3 raised to power n plus 1. Here it doesn't involve n. It means we will keep it as it is. Now write this in form of operator. This is basically e square of an minus 5 times of e of an plus 6 of an is equal to right hand side function as it is. Now take an common from here. This is e square minus 5 of e plus 6 of an is equal to 4 raised to power n plus 2 plus 2 raised to power n plus 1 plus 3 raised to power n plus 1 plus 5. Now from here we can find the characteristic equation. The characteristic equation is that is e square minus 5 of e plus 6 is equal to 0. Or in form of r we can write this is r square minus 5r plus 6 is equal to 0. What are the roots in this case? Roots are 2 and 3. Roots are real as well as distinct. So homogeneous solution is equal to first constant 2 raised to power n plus second constant 3 raised to power n. Now we can move towards the particular solution. For that we can write this is equal to an is equal to 1 upon e square minus 5 of e plus 6 into 4 raised to power n plus 2 plus 2 raised to power n plus 1 plus 3 raised to power n plus 1 plus 5. After this, we need to multiply this operator with each and every term. Plus, we also need to distribute this operator with this constant. In this case, we are getting it is like a constant raised to power n, and in this case, we replace e with 4. And this will give you 1 upon 4 square is 16 minus 20 plus 6, 4 raised to power n plus 2. Check it whether this is a case of failure. This is 16 plus 6 is 22 minus 20 is 2. So this is equal to 1 by 2 4 raised to power n plus 2, and this is not the case of failure. In the next case, it is 2 raised to power n plus 1 means constant raised to power n. It means in this case we can replace e with 2. When you replace e with 2, what we have? 1 upon 4 minus 5 into 2 is 10 plus 6. 2 raised to power n plus 1. Now this is the case of failure because 4 plus 6 is 10 minus 10, this is 0. So here we are getting a case of failure. Now before going forward, let's check it for the next case. In this case, this is constant raised to power n plus 1. So here we replace e with the constant, that is 3. So replace e with 3. We have 9 minus 5 into 3 is 15 plus 6, 3 raised to power n plus 1. 9 plus 6 is 15 minus 15 is 0. So this is again a case of failure. Now what about the next term? In the next term we are getting a constant. Till now we have done only a one case, that is the b raised to power n form. Point is, can we convert this constant in this case? For what value of b we can write this is equal to 5 as it is. So in this case we can write this is 1 raised to power n. So whenever we have constant, we can convert this into the case of 1, that is constant raised to power n, just by multiplying 1 raised to power n. And in this case we can replace e with 1. When you do so, we will have 1 minus 5 plus 6 into 5. And this 1 raised to power n is 1. And if it is multiplied again with 5, we will get as it is 5. So from here we have 7 minus 5 is 2. So we are getting in this case plus 1 by 2 into 5. Now what about these two cases? Whenever we are getting a case of failure, first step is rewrite this one in form of factors. As we can observe, from here we are getting the two roots, that is 2 and 3. It means this can be written as e minus 2 into e minus 3. So in place of this, first we will keep it as 1 upon e minus 2 into e minus 3, 2 raised to power n plus 1. And even in this case, we can keep it as e minus 2 into e minus 3, 3 raised to power n plus 1. And the rest of the things are as it is. So we can write from here this number as it is, 1 by 2, 4 raised to power n plus 2. In this case, due to this factor, it is getting a case of failure. So here we will apply the concept of case of failure, and here we will replace e with 2. Means here instead of writing a case of failure, we will keep 1 upon 2 minus 3 as it is, and for e minus 2 we will take its power is 1. It means we need a factorial polynomial of power 1 divided by 1 factorial, and this is changed by negative 1. The same concept is applicable in the next case. Due to this factor, it is getting 0. So here we will apply the case of failure. But in this case, e is replaced by 3 because it is not getting a 0 because of substituting e is equal to 3. And for this one, its power is 1. So we can take the factorial polynomial of degree 1 divided by 1 factorial, and the change here we have n plus 1 minus 1, and this term is as it is. And here we will put the plus sign. Simplify this. This is equal to 1 by 2, 4 raised to power n plus 2. N raised to power 1 factorial polynomial is equal to simply n by 1 minus 1. 2 raised to power n plus, in this case 3 minus 2 is 1. N raised to power 1 factorial polynomial means we just need 1 terms from the factorial. 1 into 1 into 3 raised to power n plus 5 by 2. And this is the final particular solution in this case. And after that we can write the general solution by adding these two solutions. That is the value of an. Let's consider this case. We need to find the particular solution for this case. This is basically a case of failure. In this case, why it is getting a case of failure? Because when you replace e with 2, we are getting a 0. But this is not getting 0 because of this. So in this case, what we can do? Here we will replace e with 2. And in this case, we will apply the case of failure. For the case of failure, we need to take the powers. So as here we can observe, 2 is occurring 5 times. So we need to pick this power. According to this, we need to take the factorial polynomial 5 by 5 factorial, and the change in this case is n minus 5. Break this one again into the normal polynomial by writing this into the factorial form, where we consider only 5 terms starting from n, then n minus 1, n minus 2, n minus 3, n minus 4. Here we have the 5 terms divided by 5 factorial into minus 6, 2 raised to power n minus 5. Moving towards the next case. The next case is when we have the non-homogeneous function of the form sine alpha n and cos alpha n. In this case, first step is we need to write the exponential form of sine alpha n and cos alpha n. Now what is the exponential form of sine alpha n and cos alpha n? So let's start from the derivation. We know that e raised to power iota theta is equal to cos of theta plus iota sine of theta, and the value of e raised to power minus iota theta is equal to cos theta minus iota sine theta. Now when you add these two equations, we will get the value of cos theta, and when you subtract these two equations, we can find the value of sine theta. Let's find the value of cos theta from here. By adding these two equations, this term is get cancelled with this one, and we can write e raised to power iota theta plus e raised to power minus iota theta. This is equal to double of cos theta, because when you add these two terms, we will get a 2 here, and the value of cos theta is equal to divided by 2 here. So from here we can derive the value of cos theta just by adding these two one. Now subtract these two one. It means the sign has changed. This is positive is get converted into negative, and the negative is get converted into the positive. So when you add these two one, cos theta minus cos theta is 0, and this is equal to e raised to power iota theta minus e raised to power minus iota theta. This is equal to double of this term, that is 2 iota sine theta. After that we can find the value of sine theta, that is this term divided by 2 iota. So very first step is we need to write the expression of sine and cos in terms of exponential. Here we have considered the theta, but as per the situation, theta is equal to alpha times of n. So the first case in this case is we will write the function with sine alpha n and here as a cos alpha n. Write the value of sine alpha n, that is iota theta, here it is iota alpha n minus iota theta, it means minus iota alpha n divided by 2 iota, and this term is as it is. Same we can mention in terms of a cos, but the change is rather than 2 iota in a denominator, there is a difference here 2, and here we have taken the negative sign, but in cos we have positive sign. Rest of the things is as it is. Then we will take this 2 iota outside because this is a constant and distribute this operator on both the terms. And similarly we can write in this form 2 taken outside, distribute this 1 by fe with this term and this. After this we can write this as this. It is like e raised to power a into b, that can be mentioned as e raised to power a whole raised to power b. So here we have taken n in a power form in both the cases, even in this case. Now we can write this is equal to b1 and this is equal to b2. So the value of b1 is equal to e raised to power iota alpha, b2 is equal to e raised to power minus iota alpha. As it is a constant, it is not depending upon the index n. So it is similar to the now case 1. In case 1, when we have constant raised to power n, what we are doing? We are replacing e with that constant, and the same step we are going to follow in this case. Replace this e by b1 and this e by b2. After that, back substitute the value of b1, that is e raised to power iota alpha, and b2 is e raised to power minus iota alpha. And this is the final particular solution for the case of sine. And the same step we can follow in the case of cos. Here we can write it as a b1 and this is as a b2. So we will get this form. Then replace e with b1 in this case and here e with b2. After that, back substitute value of b1 is e raised to power iota alpha and b2 is e raised to power minus iota alpha. The difference between these two one is there is a 2 iota and here we have 2. Here it has negative sign but it has positive sign. Now we are moving towards the question where it contains the sin alpha n and cos alpha n case. Taking the first example, solve the recurrence relation this. The first step is we need to take this term on the left side. We can write an minus 4 times of an minus 1, that is equal to negative of cos of n minus 1. Now we need to check whether the index is negative in this case. Yes. So we need to figure out for this one, if this index is negative, we will use the shift operator. So in this case, we are going to apply the shift operator one time. So apply shift operator once. It means your n index is changed to the n plus 1. So here we can write a n plus 1 minus 4 times of a n plus minus 1, that is equal to negative of cos n plus 1 minus 1. This is equal to a n plus 1 minus 4 of a n is equal to minus cos of n. Now write this back into the operator form. We can write this is e of an minus 4 of an, that is equal to negative of cos of n. This implies e minus 4 an is equal to negative of cos n. From here, the characteristic equation is e minus 4 is equal to 0, or in r form we can write r minus 4 is equal to 0. The root in this case we have only one, that is 4. And the homogeneous solution we have first constant, first root raised to power n. Only one root is there, that is the solution in this case for the homogeneous case. But for the particular solution, what we need to do from here, we can write a n is equal to 1 upon e minus 4 negative sine of cos n. So the first step in this case, we need to write this into the form of exponential. So we can write this as equal to 1 by e minus 4 negative sign outside, e raised to power iota theta, that is n, plus e raised to power minus iota theta, that is n in this case, divided by 2. Take 1 by 2 outside with the negative sign and take this operator inside this one. So we can write 1 upon e minus 4 e raised to power iota n plus 1 upon e minus 4 e raised to power minus iota n. This is equal to minus 1 by 2. So here we can write this as in form of power n, and even we can write this as power n. So the value of b is e raised to power iota, in this case e raised to power minus iota. So here we will replace e with exponential power iota minus 4, this is as it is, plus here replace e with exponential power minus iota, and this is as it is. And that is the final. Next example is solve the recurrence relation this. The first step is we need to observe whether all the sequential term is on one side. Here it is already there. There is no need to take the sequential term on the left hand side. Second step, we need to observe whether it contains any negative index. Here we have n plus 1, here n. So it means all the indexes are positive. Do not get confused by this term. We just need to figure out whether the index of the sequential term are positive or not. If they are positive, then we will not apply the shift operator. Otherwise, accordingly, we will use the shift operator. In this case, we can directly write this is e of an minus 4 of an is equal to sine n minus 1. Take an common, we have e minus 4 an is equal to sine of n minus 1. From here the characteristic equation is e minus 4 is equal to 0. This implies r minus 4 is equal to 0. Hence we have the root r is equal to 4. So in this case the homogeneous solution is equal to constant times of root raised to power n. Now we can evaluate the particular solution. So particular solution is evaluated as 1 upon this operator, that is e minus 4 sine of n minus 1. As we have learned the formula for the sine alpha n, but not the case of sine alpha n plus some constant. So in this case, first we need to expand this. For that we need to use sine a minus b form. So sine a minus b is equal to sine of a cos of b minus sine of b cos of a. To substitute the value of a as n and b as 1. We have 1 upon e minus 4 sine n into cos of 1 minus sine of 1 cos of n. Now separate these two things along with the operator. We can write cos 1 is a constant, take it as outside. Take 1 by e minus 4 with sine n minus sine 1 is constant as it is. Take this operator over the cos of n. Now convert sine and cos in exponential form. Sine theta is equal to, that is, e raised to power iota theta minus e raised to power minus iota theta divided by 2 iota. And cos theta is equal to, here we have plus and here we have only 2. So we can write direct values here. This cos 1 as it is, 1 upon e minus 4 as it is. We can write in this case as e raised to power iota n minus e raised to power minus iota n divided by 2 iota minus sine 1 as it is. This operator form is as it is. Cos of n is e raised to power iota n, rather than negative sign it contains positive sign, divided by, rather than 2 iota it has 2. Now again take this constant outside and operator get distributed over these two terms. So we can write cos of 1 by 2 iota 1 upon e minus 4 of iota raised to power n minus 1 upon e minus 4 e raised to power iota power n minus sine 1 by this constant to outside. Distribute this operator over both the terms. So we can write this as power n form. Even in this case we can write in the power n form. Now it get converted into the case number 1, constant raised to power n, and in that case we replace e with constant. So we can write directly from here cos of 1 by 2 iota 1 upon e is replaced by exponential power iota minus 4 as it is, and this term is as it is, minus 1 upon, here e is replaced by exponential power minus iota minus 4 as it is, and this term is as it is, minus sine 1 by 2 into 1 upon Again, e is replaced here as exponential power iota minus 4 e raised to power iota raised to power n. In this case, e is replaced by exponential power minus iota minus 4 e raised to power minus iota raised to power n as it is. And this is the final solution in this case.